Leaked files published by InformNapalm on November 4, 2025, indicate that Russia is using components derived from the Su-57 fighter jet for its classified PAK-DA strategic stealth bomber program. The files describe hydraulic actuators and geared hinges identified as 80RSH-115 and 80RSH, two systems that control internal weapon bays while reducing radar visibility. These files also highlight that sanctions on OBKM and limited access to high-precision machine tools continue to slow component production and testing schedules, which now stretch to 2027. InformNapalm's OBKM leak describes internal subsystems, including hydraulic actuators and geared hinges labeled 80RSH-115 and 80RSH, used to open and close the aircraft's weapon bays. These mechanisms form part of the bomber's internal armament architecture designed for low observable operation. The documentation also established a link between these components and similar hardware used on the Su-57 fighter jet, showing an effort to reuse components across different aircraft. Russia's defense ministry continues to manage the PAK-DA's development under strict secrecy rules, as it includes provisions that allow contracts to be terminated upon disclosure of classified material. While the leak confirms steady progress in subsystem completion, it also highlights industrial dependencies tied to high-precision manufacturing and ongoing delays in domestic machine tool production, both of which directly influence the project's pace. The leaked data revealed that production targets are now distributed over several years, from component fabrication to prototype integration, with 2027 serving as a provisional marker for early serial readiness. The hydraulic and geared hinge assemblies play a critical role in ensuring that weapon bay doors operate quietly and reliably under aerodynamic stress, a key requirement for stealth performance. The manufacturing tasks are concentrated among a limited number of suppliers responsible for both fighter and bomber mechanisms. Despite domestic support measures, shortages of advanced machining tools continue to pose difficulties for large-scale production. The EU's decision on October 23, 2025, to sanction OBKM, a primary manufacturer of these assemblies, further tightened import channels for machine tool accessories and materials. Combined with prior restrictions on precision equipment, this move directly impacts Russia's ability to sustain the desired output rate, making industrial capacity the decisive factor in the program's schedule stability through the mid-2020s. The PAK-DA's origins date back to the late 1990s, when the Russian Air Force began examining a long-term replacement for its Tu-95MS and Tu-160 bombers. In 2007, the Defense Ministry formalized the technical assignment, and by 2008, financing allowed for design studies to begin under the supervision of Tupolev. In 2013, the configuration was finalized as a subsonic flying wing, emphasizing low observability and internal payload capacity rather than supersonic dash performance. Construction of specialized production infrastructure at the Kazan aviation plant began soon after, with tool installation and prototype work packages gradually proceeding through the 2010s. Early targets for a demonstrator flight by 2023 proved unachievable, with subsequent internal goals shifting toward ground trials followed by potential flight testing later in the decade. During this period, Russia pursued upgrades of existing bombers, the Tu-160M2, Tu-95MSM, and Tu-22M3M, to preserve strategic coverage until the new aircraft reaches operational readiness. The continuous evolution of PAK-DA demonstrates a shift in doctrine from speed-based penetration toward endurance and standoff engagement through low observable design. The airframe is planned as a large flying wing with a 4-person crew and significant internal volume for fuel and munitions. Estimates indicate an empty weight of about 52 tons and a maximum takeoff weight approaching 145 tons, making it comparable in scale to the USB-2 Spirit. The unrefueled range is expected between 12,000 and 15,000 kilometers, enabling intercontinental missions without aerial refueling. Its payload is projected at 30 to 35 tons, distributed across 2 or more internal bays. The service ceiling should reach up to 20,000 meters, and cruise speed is defined around 800 to 900 km per hour, reflecting a subsonic profile optimized for radar avoidance. The operational endurance goal stands near 30 hours, supported by onboard systems designed for extreme environmental conditions ranging from -60 to +50 degrees Celsius. The overall performance balance prioritizes range, mission persistence, and low signature over maximum speed or agility, allowing the aircraft to remain outside hostile radar networks while launching standoff weapons. Structurally, the PAK-DA integrates composite materials and radar-absorbent coatings designed to minimize reflection and thermal emissions. The airframe's continuous leading edges and internal weapons bays eliminate external pylons or protrusions that would otherwise increase radar cross-section. The tailless flying wing design requires an advanced digital flight control system to maintain aerodynamic stability across all flight phases, especially as the aircraft's center of gravity shifts during weapon release. The internal framework must support large bay openings while remaining stiff enough to prevent vibration under high dynamic loads. The aircraft's outer panels are designed for easy maintenance while preserving stealth features, and edges are aligned to reduce electromagnetic returns. The engines are buried within the fuselage, with air inlets shaped to conceal compressor blades and exhaust ducts flattened to limit infrared visibility. Every structural feature contributes to a low detection probability across radar, infrared, and acoustic spectrums. Avionics and mission systems are focused on multi-sensor fusion and passive detection. The aircraft is expected to feature a low probability of intercept radar system for terrain following and mapping, infrared search and track sensors for detecting enemy aircraft, and passive electronic support measures for situational awareness. Its flight control architecture is built upon a fly-by-wire system adapted from contemporary fighter technology but expanded for the stability demands of a tailless platform. The bomber's electronic warfare suite prioritizes deception, emission management, and self-protection rather than broadband jamming. Secure communication and data links will allow coordination with airborne or ground assets over long ranges, supporting potential networked operations. Some design proposals suggest the PAK-DA could serve as a command node for unmanned aerial vehicles or act as a control hub for decoy drones, expanding its role beyond traditional strike missions. Overall, the avionics configuration emphasizes automation, navigation accuracy, and reduced crew workload during extended endurance flights. Armament integration revolves around an all-internal configuration to preserve radar stealth. The PAK-DA is expected to deploy the KHBD long-range cruise missile with an estimated reach of 6,500 kilometers, alongside the KH-101 and KH-102 for conventional and nuclear missions. It will likely retain compatibility with older missiles such as the KH-55 for flexibility in mixed-load missions. Russia also plans to integrate new hypersonic systems such as the KH-95 once testing progresses to maturity. Internal bay geometry allows for standoff weapon deployment across different payload combinations while maintaining aerodynamic stability. Some design provisions anticipate limited carriage of short-range air-to-air missiles for self-defense during solo operations. Weapons separation trials will be among the most critical test phases, as aerodynamic disturbances in an enclosed bay can affect safe release. The armament strategy positions the aircraft as a missile carrier capable of executing precision strikes from far outside air defense coverage, rather than as a bomber conducting direct penetration attacks. Propulsion will be provided by two modified NK32-02 engines derived from those used on the Tu-160M2, adapted for sustained subsonic cruise. Each engine is expected to deliver roughly 14,000 kilograms of thrust in non-afterburning mode, optimized for long endurance and low fuel consumption. The propulsion system must function efficiently at both high-altitude cruise and low-level penetration while minimizing radar and infrared emissions. Intake geometry is configured to conceal turbine faces, while the exhaust structure includes flattening and temperature mixing features to reduce thermal signature. The engines are integrated into the fuselage with modular accessibility for maintenance without compromising stealth coatings. The propulsion choice leverages existing production lines, limiting technical risk while ensuring power consistency for electrical and environmental systems. Operationally, this configuration supports endurance-oriented missions rather than high-speed dashes, aligning with strategic doctrines that rely on standoff missile employment from distant launch points beyond adversary interception range. Delays in the PAK-DA program stem from several interconnected constraints. Precision manufacturing remains the most significant bottleneck, as many specialized components require machining capabilities previously supplied by foreign vendors no longer accessible under sanctions. The October 2025 sanctioning of OBKM further tightened control over tooling imports and slowed production of critical hinge and actuator assemblies. Concurrently, limited domestic capacity for advanced composites and avionics has stretched timelines for subsystem integration. Competition for skilled labor with other aircraft programs, including Su-57 and Tu-160M2 modernization, adds additional pressure. Testing schedules could face further setbacks if weapon separation or engine endurance trials encounter anomalies, as these cannot be accelerated without compromising safety certification. The complex nature of stealth coatings and internal bay mechanisms introduces additional verification steps. If these production and testing constraints persist, achieving serial readiness by 2027 may require revised staging or lower initial production volumes. When compared with U.S. stealth bombers, the PAK-DA shares key characteristics with both the B-2 Spirit and B-21 Raider. Like its American counterparts, it adopts a flying wing configuration, subsonic cruise, and an internal weapons layout to minimize radar visibility. The B-21 benefits from newer composite materials, next-generation mission software, and advanced networking capabilities that integrate it into broader air combat systems. The PAK-DA's design focuses on greater payload flexibility and endurance rather than cutting-edge digital integration, reflecting the difference in technological and industrial ecosystems. The American aircraft's production is backed by a larger and more automated industrial base, which reduces risk compared with Russia's reliance on fewer domestic suppliers. The Russian platform, however, compensates with extended range and compatibility with long-range cruise and hypersonic missiles that can be launched well outside engagement envelopes. Operationally, both aircraft serve the same strategic role, delivering deep penetration or standoff strikes against heavily defended targets. When compared to China's H-20 project, both are subsonic flying wing aircraft designed for low observability, long endurance, and internal weapon carriage. The PAK-DA's projected range of up to 15,000 kilometers and payload of about 30 to 35 tons would make it competitive within the same class if achieved. The Chinese program benefits from broader industrial resources and access to modern electronics manufacturing, potentially accelerating avionics integration and serial production. Russia's program, constrained by sanctions and import restrictions, must rely on domestic substitutes for key systems and materials, which may limit pace and efficiency. While both designs aim for survivability through stealth and standoff engagement, their production realities differ sharply. The H-20's eventual performance will depend on how successfully China integrates hypersonic or advanced cruise missiles, while PAK-DA's success will hinge on sustaining a stable supply chain and completing the integration of propulsion, sensors, and weapons without further delay.